Okay, so welcome everybody. I'm Paul Valdez. I'm part of the Pages steering group, and also have been heavily involved in PMIP right from its very start 30 years ago. And some of you may know that we've been celebrating the 30th anniversary of PMIP this year, and I'd recommend you go and have a look at the Pages newsletter or Pages magazine, which features the PMIP work. But it's my pleasure today to introduce Chris. I really realized Chris was probably still in school when PMIP started 30 years ago, but it's really great to see a kind of new generation of scientists working on the PMIP project, and hopefully going to see a long future. So Chris started his research life in Reading and doing his PhD, and then moved over to Yale, where he spent a number of years working on a variety of different topics, mainly in the sort of paleoclimate domain. And he moved over to UCL in what was it, 2011, is it, or something like that?
Yeah, nearly 10 years now.
Yeah, goodness me, time does fly. Where he's been rapidly promoted to now Professor of Climate Science. He's been incredibly heavily involved in lots of different activities, very heavily involved in IPCC, where he helped prepare some of the paleoclimate work within the report. And so he's got a lot of experience now in terms of using, well, both running the models, but also using PMIP output. And it's this which I am very much looking forward to hearing about today. So over to you, Chris.
Thank you very much. So I think what I'll first do is there's a poll going on. So I'm going to end that and let everybody see what the results are. About not quite half of people have answered, but the things seem to be staying stable. So as a climate modeler myself, obviously I do quite a lot of coding, but I recognize that not everybody is somebody who does lots of coding. But obviously this is about data, so I'm trying to think about how to pitch the level, and there are some people who know a bit of coding and might find that side useful, but there's obviously some who would prefer even easier access. And so I'll try and address both of those. They're slightly different tools. And then about 60% of the people who answered say they do computer work, so that's fine. But there's obviously a smattering of people who do stuff in the lab and in the field. And therefore, I think my suspicion is they might correlate with those who don't do the coding. So obviously, there are only certain time periods in that have been run already in PMIP, and although people will run models, you can collaborate with scientists and they might run a model specifically for you. In general, I think the useful thing about PMIP is the fact that everybody has done the same experiment, and then then shared all their results, and so you can't have you can't be questioned by reviewers. Oh yeah, but that's in your one model, what about all the other ones? And so it has the advantage of having that multi-model side of things. Sarah's shared the time periods of interest, and so there's clearly some Holocene and some last 2,000 years. So I'll mention most of those. The deglaciation, I wasn't planning on talking about, but there are a few long transient simulations going right the way through it, but they're not really freely available, but they do exist. And we can give people connections to who the researchers are that can provide you with data for that. Okay, so the next thing I was going to do was going to share my screen. So here we go. So sort of I've said some of this already. That was just me reminding myself that I'm going to start. What I'd like to talk about in this session is just give you a bit of background about PMIP and what's been done and what's available. And hopefully that'll take about third of the session, and then I'd like to show you how to find some of that data that's been lodged and stored, and that's using something called the Earth System Grid Federation, or ESGF. And then we'll play with using the interactive atlas, and then if there's time I'll go into some other ways that there's more sort of other data, and I'll wrap up with a sort of my advised process for getting hold of climate model data. This is more just to remind me that when I say climate models, I mean something that is basically like a weather forecasting model. So it's a dynamical model derived from the physical equations, and it's not something that's driven by data. So these are the same systems that are used for future projections. And in fact, for most of the ones we're talking about today, the PMIP ones, they are, I haven't said that PMIP is but the Palaeoclimate Model Intercomparison Project. There's a hell of a lot of acronyms, I'm sorry. But the PMIP ones are explicitly the same models that have been used to make future projections, with the intention that by analysing the past response, we can learn something about the quality of that model's future response. And so that's what these models are. When it comes to thinking about them in a paleoclimate context, I think it's sometimes helpful to think about quite what these models are doing and some of the timescales and what's included and what's not. So a climate model, generally, you're going to be having an atmosphere. The atmosphere, I've put some timescales on here for how long it takes for that component of the climate system to feel the full effects of some change. And so once you change something in the atmosphere, you need to run it. You need to run your model for about a year, but that's only because the information will travel around much more rapidly than that. But it would just be a bit strange to try and run a model for less than at least 1 year because of the strong seasonal cycle in it. And then, so all models will have an atmosphere. They'll then have an ocean underneath it, and although there are different timescales in the ocean, sort of the tropics, the upper ocean in the tropics, you're thinking quite short timescales down to some long, very long 1,000-year, maybe more timescales on the abyssal ocean. There will be a whole ocean attached to this atmosphere, and the ocean will go right the way down to the depths. But whether the simulation will have run for long enough to bring some of to allow those bottom waters to have really felt the information, the sort of the conditions that have been imposed or given to the model, is often not the case. There's going to be changes in the continent. None of the models, or all the models, have a fixed orography as they're running. Generally, they're sort of the orography is imposed on the model. There are some simulations where you might run for 1,000 years and then change the boundary conditions. That's what we have to do when we do deglaciation ones, and you sort of change the ice sheets and the boundary conditions, and they're generally on long time scales. And for PMIP, just sort of this subset of past climate models, because they're the ones that are used for the future projections, they generally don't have big dynamic ice sheets and changes in orography, because those aren't going to grow, and you're not going to see sort of Laurentide ice sheets over the next 100 years. And so they're not needed for the future where these models are being built for specifically, and so they're not going to be included in these simulations. But as paleoclimate researchers and modelers, there are people really interested in these questions, and so there are now coming online models that have elements of this in a dynamic fashion. All the models will have some sea ice. They'll all have some component of the biosphere, because you need something green that loses its leaves to get even just the color of the planet right. But how interactive that biosphere is going to depend on, again, I suppose, really what the conditions of the model developers were thinking when they wrote the model for the future. And clearly, vegetation is not going to be allowed to develop naturally in the coming 100 years. There will be some strong anthropogenic influences on it. There's a couple of things that we as modelers, or that you might consider as part of your Earth system, but we're consider as external to the climate system. And those are solar input seems external to the climate system as well, sort of be that orbital variations or the amount of or variations due to sunspots. So that's external to the climate system and needs to be given to the climate model and imposed upon it. The other one is volcanoes and volcanic ash going up into the stratosphere. That obviously has a strong climate impact, or a climate impact, and is one of the strongest forcings over in paleoclimate times. We treat that as external to the climate system because there isn't a because the model isn't sophisticated enough to be able to form predictions of sort of interactive predictions of when those volcanoes happen. And I don't think any, and if geologists could find a nice way to predict volcanic eruptions, then that would be wonderful. But it hasn't happened yet. So that said a bit about what the climate system is and what the models are trying to represent. What I want to do now is show you this nasty slide with two different bits of things with various bits of acronyms. So the MIP is a model intercomparison project, and so I'm talking about the Palaeoclimate Model Intercomparison project, which is didn't want to do that, which is, and we're now on to the fourth phase of that, which confusingly is a subset of the sixth phase of the coupled model intercomparison project. And so here is what the coupled model intercomparison project is. And basically, I suppose it's a way of submitting your new climate model, and then you need to, once you've built your climate model, you need to do some standard scenarios, and these are referred to as either as the DEC, for an acronym that's in German, I believe. And so they have to do some standard things to allow people to assess how good their model is, and then you can start thinking about what experiments you want to do with your model. And clearly, the vast majority of people doing modelers want to look at future scenarios, and so they participate in a project of scenario MIP. We're here interested in paleoclimate runs, and so you would use your model that's developed for the future to run for paleoclimate timescales, and that makes you part of PMIP. Things get slightly more confusing in that I'm going to talk about I've explained PMIP as being a subset of this wider effort to develop new models. Well, that's true, but there are also other climate models out there that aren't brand new, but still have a lot of use and can tell us an awful lot about paleoclimate. And that's partly because the brand new models are optimized to run for 100, maybe 200 years. And so running them for thousands of years becomes computationally really challenging and takes a long time. And so it's actually, and as the models aren't necessarily an awful lot better than the previous generation, you can learn things using an older model, but using those computer resources to run it for longer or something like that. And so there are models that sit outside of the brand new model framework, so the CMIP6, and they can run experiments and do things. I'm going to talk about this bit, which is the intersection between them, and then my next plan is to go through some of the acronyms and explain what the simulations are. So this intersection bit, which I'm going to give the catchy name of PMIP4, CMIP6, all as one blob. There are a bunch of simulations that have been run with these models, and so I said about the sort of the standard simulation, and so these are the grey ones. And the standard simulation is you need some control run, which by convention is a pre-industrial control run. And by that, it means pre-industrial as in constant 1850 conditions. And then you want to see how your climate model compares to observations and develops over the historical period. So you start off in your 1850 conditions and you run that for a long time. And then at some point you branch one off and you use a historical run where you're using all of the forcings that have been observed over history. And so that's free running. And what I mean by that is the noise within the climate system shouldn't match with observations, because both the models and the observations are having different realizations of the noise. So you shouldn't be comparing sort of ENSO in 1998 with an ENSO with the state of ENSO in 1998 in the model run, but the statistics should be right. And so those are sort of those two runs, and they're quite helpful. Then there are two idealized warming runs, one where you instantly quadruple the level of carbon dioxide. That is primarily designed as a model to allow people to compute the climate sensitivity of a model, sort of a standardized, and although it requires more computing time to do it, it's quite easy to code up and run and standardize. So that's what that one is. And this is a very crude scenario run, but again, one that doesn't involve many choices by different modeling groups. So it's a very clean intercomparison between the models, and it allows you to tell something about the sort of the speed at which climate change happens, whilst this one tells you about where the model's equilibrium state. So so those are the standard ones, and then obviously there are various scenarios of future projections coming down here, and they're forming part of this scenario MIP. And then these ones in orange are the ones that are specifically for PMIP. And there are, and I guess there are two, or that there are a few ones that are these four sort of come in a slightly different class than the others, just because of their I was going to say ease to do, but how many models have done them and where their data is stored. And so these are all aimed at equilibrium runs, or maybe snapshot is a better perspective. So there's the two long-standing ones that have been in PMIP since the very beginning, so for 30 years. There's an experiment of the mid-Holocene, which in our cloistered world we think of as 6,000 years ago. And so it's not aiming, it's sort of, if you imagine the whole Holocene and you've run the whole Holocene with your model, you've zoomed in on that little bit at 6,000 years ago and just extracted it, and you're just doing a snapshot just of those conditions. And so the model runs forward in time, but the forcings don't change. So irrelevant of how long the model run is, the orbital conditions and the other factors that drive climate are all staying at 21,000 years ago. And then there's a simulation of the last glacial maximum, which again, in model world, this is 21,000 years ago. A new simulation that's been brought in this version of PMIP, but wasn't official in any of the previous ones, is a model of the last interglacial. And in this case, the decision was taken to go for 127,000 years ago. And whether that's, and I'm sure that's not representative of the whole of the last interglacial, but that's when it is, it's 127,000 years ago. And then there's a simulation of the mid-Pliocene, which is 3.205 million years ago in this case. So again, these are all snapshots that look in. There are an additional sort of slightly outside of the main PMIP, of the main framework, there's efforts to look at the early Eocene in something called Deep MIP, where those model runs are all available, but they're available on a different server than the sort of the more official routes that I'm going to show you. And that's mainly because these simulations have been performed by models that are not the whiz-bang models that have been developed for looking at the next 100 years. There are some transient simulations. So there's a simulation of the last millennium, which runs up to 850, or it starts at 850 and runs up to 1850, and then you can stitch on the correct historical simulation. There might be some jump between them if you run them separately. And there's a last deglaciation experiment and some simulations going on. But again, these are not easily available, but they exist. There's two simulations for the past 1,000 years, and then there's another one that actually extends back to the past 2,000 years. and that's readily available. And so the next thing I'll do, so that's sort of hopefully said what model runs people are doing sort of in this project. The next thing I'd like to do is to talk about where all of this data is contributed. And so individual modeling centers will run their model and store their data in the way they store their data. And for some modeling centers, such as NCAR, that involves putting it on a server that could be accessible for the public. And so there is more data available on individual servers in the format that that modeling group has chosen to use. The most useful set of data, and sort of the core set of data, I suppose, comes through this thing called the Earth System Grid Federation, which is a distributed network of large data servers. And that's what the federated means, which for those of you long enough in the tooth means it works a bit like Napster to share, that was there to share music. But so each server will have a batch of data, and together all of the servers will have a spare copy of the data, but not every server will have all the data, just because there's so much stuff. There's roughly, I think there's about 16 petabytes of data. So this is a massive amount of data, and many of that 16 petabytes will be stored multiple times. What is advantageous about this system, though, is that there's a single tool, and I'm showing you a version of this, a screenshot of this, where you can search for all of the data through all of the data that's available, and so although all the data is sat on these servers around the world, you just need to go to a single location, and it will then sort out where it all is and find ways for you to be able to download it. The other thing that is vital for saving time for everybody really is that all the data is stored in a common format, and that means it's stored with a controlled vocabulary. And so whatever metadata is stored, or all of the variables are going to be called the same thing, and all the files are going to be in exactly the same format with the same variable names, and the dimensions will be called the same thing, and they'll be stored in the same structure for each model, so that once you've written a piece of code that can deal with the information from one model, then you just need to point it in a different direction, and it will be able to cope with analyzing the output from all the models. And this sort of convergence on standards is an absolutely vital thing that is a bit of a headache for when you run your model and then convert the data into that standard format, but is so useful for all of the researchers down the line. The particular format that all of these data is stored in is something called netcdf files. And in this case, they are climate format compliant netcdf files. And so they are something that there's many different ways to open these files. It's fairly standard, and it's really popular within the climate field. It's not so popular outside of the climate field, but nonetheless, anything you want to do, there'll probably be a tool that does it. This is what data's on the server at the moment, and so this for the PMIP simulations. Obviously, if you want to use some of the data and look at, say, the changing climate between the mid-Holocene and now, then you can't just download the mid-Holocene simulation, because that only tells you the climate in the mid-Holocene. You also need to download the control simulation, so the pre-industrial control. So there is another experiment that's not being shown in this table for the pre-industrial control, but all of the models have that pre-industrial control, because otherwise they're not allowed to be part of this data service. So there are 17 models in total that have done PMIP simulations and lodged the data on the Earth System Grid Federation. The most popular experiments, the two interglacial ones, this is mid-Holocene and the last interglacial. Those experiments are functionally quite easy to set up. They're not easy, but they are much easier than the other ones. Setting up a last glacial maximum experiment involves changing lots of different bits in the model, and some models just can't cope with it because the climate is so different than the present day. So unfortunately, only 4 models have done a last glacial maximum experiment, and there are 6 that have done a mid-Pliocene experiment and posted their data. And with the past 1,000 years and the past 2,000 years simulations taking longer to run, people are still working on those, and so hopefully there will be more of those posted later. But there's a variety of different other data that's already available for those, and I'll hopefully get time to mention that at the end. So what's being shown in the numbers here is how many data sets, and so that is how many variables for nearly all of these simulations, other than I think this particular IPSL one. Only one instance of each model has been run. So say the CESM model has run for the mid-Holocene, but it's only run once, and that run might be sort of a few hundred years, but there aren't multiple different realizations of that climate. And so for most of these, this number is actually showing the number of variables that are available for them. So I think I've said something about that. What I was thinking might be best to do next is if I stop sharing this and jump to sharing my screen instead. So, and then we'll go and have a go at finding some of this data. So if I just share my web browser and and then make it a bit bigger, hopefully, so that you can see the size of the text. Okay, so I've logged in. This is the Earth System Grid Federation server. I've already logged in and into the CMIP 6-bit, and then I'm presented with a web page that looks something like this. And there's no results to start off with. And because there's so much data, the default is that you're not searching for anything until you've selected that you've started to search for something. And so what you would do, I thought I'd run through it because I know that I'm familiar enough with it that I know where to press buttons, but it's it's not immediately obvious what all of these terms on the side panel mean. So if we go to activity to start off with, and then we can find PMIP as an activity. And so I can tick it and then go search, and shows me some search results. Is everything else all right? Yeah, okay, good. It did have quite a long think, obviously. That's maybe because there's so much data it needs to sift to. I'm sitting using the one in Britain, the CEDA server, but you can use whichever one is nearest to you. That's the recommendation. So this is all of the PMIP data, and it's found all of the data lodged associated with PMIP. For this example, I'm decided that I'm going to look for the Atlantic meridional overturning circulation during the last interglacial, and I'm only going to look for it in one single model. But so I want the last interglacial, so I open up experiment ID, and then I can select the last interglacial, which in this case is given the code of last interglacial based at 127,000 years ago. So I select that, and then I go search again. The purpose of doing the search each time is it filters not only the text over here, but will also filter all of the options under these drop-down menus. And so I'm constraining as I go along. So now I'll pick a particular model, And so for reasons unknown to me, the model name is actually called source ID. And so these are all the names of the models. And I feel with these, you can just treat them like they're a person's name and not necessarily need to spell out all of the acronyms. So I'm going to go for EC Earth, which is the model run by the European Centre, and in this case has been contributed by Swedish colleagues, and so is sitting on the data server in Sweden. So I've gone for my EC Earth, and then so now I've picked the simulation. So I picked the particular experiment that I'm going to look at, and then I need to work out how I find the AMOC in it. So I can, if I want to, I can click down on variable, and hopefully you can see over here that this is the list of variables that that is available. And you'll also see that they don't necessarily make a lot of sense. They're all official controlled vocabulary. So once you know that controlled vocabulary, you can perhaps start translating them. The most useful one to learn is TAS, is temperature of the air at the surface. And so there's somewhere there will be a TOS, which is temperature of the ocean at the surface. And so that's SST. And then there's PR for precipitation rate. But clearly these don't make sense to me, and I don't know what most of them mean, like HFib, therms, DS. I've no idea what that means. So this isn't much help for me. But what I do know is that that the AMOC variable I would be looking for is part of the ocean. So I can go to the realm and I can sort of do some filtering and say, okay, well, I know it's related to the ocean. So now if I go back to my search box, and then that's going to subset all of these variables and only look at the ocean. And so now my list of variables is shorter, but still pretty impenetrable. What you can pick instead is the climate format standard name. And so this is sort of a translation, an official translation of what those variable acronyms mean. The variable acronym is important because when you need to read the actual file, it's stored as variable, not stored as CF compliant name. And then down here, I can see that the variable I want, the AMOC one, is the ocean Y overturning mass stream function. And so I can select that, and that will show me the files. Okay, and so in this case, I've now constrained everything down, so I'm only looking at some files, and if I want to, I can see the metadata, which is all of the data that describes the information that describes the data that's actually provided, stored there, and that tells you what it's categorized as. But I can list the individual files, and here we go. So here are some individual files listed. In this case, this particular model has provided a file for every year. I can see this from the end of the run. There's just 2 years, or there's just a year here because it goes from 2,240 on the first month to 2,440 to the 12th month. And this is monthly data. I can see that from the fact it's called OMON. It's worth me pointing out at this point, when I look at the dates, that these are model years. And so with respect to the start of whenever somebody first set the model off, they don't relate to anything associated with a calendar, as you would think. This is an idealized run, in this case, of 127,000 years ago. And so these are all different snapshots of 127,000 years ago, but you need to know the various years, just so you can stack them up in order and compute sort of long-term averages and the like. So I can download this file by going HTTP download. and it should just download the file, although it tells me in this case that it can't be downloaded securely. So I'm sure there is a way for me to accept, keep. So I'm going to keep it anyway. And so it's downloaded the file, and then you can open it with whatever software you use to look at NetCDF files. On my Linux machine, I'm using a piece of, I use a program called Panoply just to visualize some of them. And here, so this program is created by NASA GIS, and it's just a point and click viewer for individual files. You can't really do anything other than look at the files and create a plot, but it does mean I can create a plot of the AMOC for this particular year, and I'll see what this looks like. No, this is not. I've picked one that's not particularly convenient. Georeference plot using level, using RLAT for the X. This, and here's a version of some stream function as plotted using it. You can not really see. I'd need to fiddle with all the various bits to show it, but there is at least some data, and there's some numbers attached to that data. And so that's just downloaded that one file. If I wanted to download lots of files, I'm going to zoom out a bit so we can see more. If I wanted to download lots of files, then I could do add all displayed results to data cart. And I've logged in. You can see my stunning username here. I've logged in, and then I've added them all to the data cart. And then I can go to my data cart, and then I can do a bulk download through something like a wget script, which allows you to download lots of things all at once. So that's how you can download data directly. So if I stop sharing that, but it's obviously quite a fair bit of work to download all of that data. And even just for that one model and the one variable, you needed to download 210 files. And that was the raw data, so that you could work on things from there. Depending on quite what you want, you might not need to download any of that raw data, and you might instead be able to just quickly get away with downloading data that's already available. And so Paul, in the introduction, mentioned I've been involved in some bits in the IPCC, and one of the bits I was involved with, informally at least, was the Interactive Atlas. And so this year, or this assessment report, is the first there's been an official Interactive Atlas. Previous years there's been a sort of a paper atlas and a load of maps that everybody could sort of cycle through and have a look. But in this report, there's actually an interactive atlas. And so that interactive atlas is clearly designed for studying future projections. This is its sort of the way they're selling it. And so it shows its possible future climates. But there is some PMIP data available in the interactive atlas. And I can go and show you. It's only in the advanced version of the interactive atlas, but there is, which you need to get to by clicking on this side. But there is some down there in the PMIP 4. There's a limited variables, and there's only 4 equilibrium simulations for PMIP 4, and there's only 2 for PMIP 3 because the last interglacial and the mid Pliocene are new simulations and weren't included in the last one. But I thought I would, having shown you how to download some data, I thought I would also show you how to go and get some data on the interactive atlas and create a map from that. So let me stop sharing this, and I'll go back to sharing my internet browser, where hopefully now I've switched to the interactive atlas. And so this is that front page of the interactive atlas that you're brought to when you just go in. And there's some bits, some videos explaining what the interactive atlas is. If you go to the advanced version of the regional information, you're brought to a map like this. And this is where I discover it's remembered all of my settings. No, it hasn't. And so if you go to dataset, you can go to Palaeoclimate. Now, there is no Palaeoclimate actual reconstructions included in this atlas I think because the formats ended up being so different that it was challenging to do it on time, but there is these model runs. And so if we want to look at the mid-Holocene, this is something I've published on, so we can go to the mid-Holocene in the PMIP4 simulations. And so you can see something's changed in the map in the background. And maybe if I make it bigger, can you see the words a bit better? Maybe, yeah. And so there's only two variables here. There's mean temperature and precipitation, and these are both showing percentage changes. So I'm going to look at precipitation, and I can go and change on the quantity and scenario to the mid-Holocene. And as you can see, the only option is that it's the change in the percentage change in rainfall between the paleoclimate scenario, in this case, mid-Holocene, and the pre-industrial control. And there's no other options for that. So it's quite constrained in what's available. And I can pick a season if I want. I can even customize it to an individual month. But this is showing the annual mean precipitation. And now if I just zoom out a bit, so the map's all being shown again. And you can see that in the mid-Holocene simulations, there is a large percentage increase in rainfall over the Sahara region. It doesn't take a lot to get a large percentage increase, because remember, there isn't an awful lot of rain over there in the first place. But nonetheless, this data is available. And if you were to pick on a region, as you saw there, I'm going to pick on the Madagascan region, just as an example. And you would see here the percentage change at each month, and there's a value for each individual model that's coming up. I don't know if you can, so there's value for each individual model and an ensemble mean averaged over that region. And so that data, if you just want some numbers to compare your proxy results to, this is probably sufficient for a temperature change or a precipitation change. And if you want the actual data or a pretty map, you can edit various bits of the color bar and the like, and zoom into the regions and change the projections. But if you want the data in the actual map, then you can go and download that as a NetCDF or as a GeoTIFF if you want to load it into some GIS software. And so this data is also available through this nice interactive website. Okay. So Emmanuel has asked if there's a possibility to download the average of the models in ESGF. Yes, if you download the field, it will only give you the average of all the models, the ensemble mean. And there's a catch in there. It'll only give you the ensemble mean of the models that are on the Earth System Grid Federation. And so for the LGM, that's only 4 models. And there are other LGM simulations that have not been run. So there is other data around that might be useful. So you can get to, where am I going now? So you could get to so we've done that. There's other pre-processed data around. The interactive atlas isn't the only source. I've made an organization, it's called, on GitHub, and that stores the files I originally provided to the IPCC authors to make the interactive atlas, and then a workflow paper that I'm showing here. And that workflow paper has said everything all the steps I went through to make the mid-Holocene paper that I published summarizing the mid-Holocene simulations, and we've applied that to all of the simulations on the Earth system grid. And I've used a package called the Climate Variability Diagnostics package, which just goes and auto computes a load of things like your ENSO record and your mean state and your AMOC. And then we've also in this paper provided some codes to analyze that and some data that we've sort of computed. And so this is currently all shared on a GitHub repository, but so it's called the Past to Future Analyzer is what I've called it, because I'm part of the Past to Future working group. And so it's got some data in data frames, which is Python's way of talking about sort of comma separated values. And so you can go and get some common measures, say, then there's then here is some changing global mean temperatures in all of the simulations, right? So this is stuff I've computed, and everybody was very generous in giving the data to the Earth system grid. And so I've tried to be generous in giving everything I've computed back as well. And we've done some things like monsoon area, and there's various different ENSO metrics, or if you want to know how the amplitude of the Indian Ocean dipole changed in all the simulations, then it's just sitting there in a spreadsheet, and you're welcome to it. The -999s mean that there was no data for that simulation. That's in effect that the modelers didn't do, or there was no model run for that. And then so that's just summary things, but there's a bunch of netcdf files you can download for all of the different simulations, and they're free to download. And then also there are some things called notebooks, which, if you're familiar with Python, are the Python code that we've used to create a figure. And here's a list of how it's all loaded in, and all of the code is there, and you run through all of these bits of code, and then it gives you the figure at the end, and this is a resulting figure. And you can download those and the data, and then go through and press play, and you will be able to make that figure yourself. But the advantage being that if you want to change it slightly, then you can. And so I think that's that. And so all of that data is free. I've got what I want from it, and people were generous to give it to me. So it's only fair that we pass it on and make it easy for people to use. The final thing I wanted to say is, I've talked all about the PMIP things. I noticed there were a few people at the beginning of the call saying that they're interested in the mid-Holocene, or they're interested in the past few thousand years. There isn't a lot of that data through PMIP, but there is an absolutely brilliant data set coming out of the CESM, which is the last millennium on Ensemble, that has run 36 simulations with a single model, running from 850 all the way to 2005. And there's 6 hourly data, and there are runs where they've just used the orbital changes or just the volcanic changes, and there are some water isotopes available on that. There isn't any water isotopes available on the Earth system grid, but obviously some models do compute isotopes as they go along. All of this data has been made available by the researchers doing the last millennium ensemble, and there's and then that same climate variability diagnostics package that I've used has been run on it, and all of the data is available. I'm going to share the PDF so you can find all the links for these. And here's just an example of the Atlantic multi-decadal oscillation in all of the simulations, and you can just download the data that's plotted here or look at the figures in that. And so with that, I think it's time for me to close my talk, I just thought I'd finish up with my suggested steps of how you go about doing it, so of sort of what hierarchy you ought to think about getting some data. So I think the easiest way, if you're not a modeler, to get some data is to collaborate, because otherwise you're going to have to do all the work and all the analysis. So if you can, talk to a modeler, and they're generally friendly, and they'll generally be happy to collaborate with you and help you make your paper stronger by contributing some data that they've already got. So if that's not there, then the next thing to ask is whether any of the PMIP simulations, the ones I've sort of talked about here, might be relevant. They're not going to be relevant for all options and for all time periods, but there might be some relevant data already out there. And then if you've decided that there is a simulation that's relevant, then I suggest you go and then you can go and see if there's any pre-processed data, maybe in the supplement of a published paper, they always exist, or the interactive atlas, I showed you how to do that, or some of the stuff I've done, and there's some scripts and data just available for that. And because that's going to be easiest. And if that doesn't work, then you can ask, is there full fields for me to analyze? And they would be available on the Earth System Grid Federation. Personally, although I've downloaded all the data, it's even easier if, rather than you downloading all the data to your computer and doing things with it on your computer, if you can just take your code that you've written and take it to the data, and then it's going to be faster and you don't need to bother with downloading anything. And so the way to do that is through something called server-side compute, and Ines has a link where you can apply for server-side compute if you need it. Otherwise, you can download that data, and there is a command line tool called Cinder that can do it, or sort of that can bulk download things if you're having problems just pointing and clicking. The final thing I wanted to say is that there's only a subset of data from all the simulations that's available, and the models have lots of fields. For example, water isotopes is not available really through anything that I've talked about today, but might be by far the best thing to compare to any proxy data. Don't feel you need to force your proxy data to do something to fit with what fields are available from the model. Think about what your proxy data is doing, and then think, okay, well, maybe if I take this bit from the model and that bit, and then combine them, and then it's only this month, and so on, then that's actually what the proxy is doing. And in a very formal way, that might be a proxy system model, but in easier things, it's probably quite simple. But those sort of things you might want to, yet again, just find somebody to talk to. And with that, I'm going to stop. But I hope that barrage of information hasn't been too much.
That's brilliant. Thank you. So that gave us a brilliant overview of what is available, and also some ideas on how to access it. There's been a few questions in the chat, so now we're opening it up for questions, and so feel free to either put a question in the chat or put your hand up so that you can ask your question online, sort of thing. Turn your microphone on. So we've got one question from, two questions being handled. One question from Ellie, talking about sort of models outside of CMIP 6, but within PMIP 4, and how do you get hold of the data for that sort of thing, basically?
Well, they're not on the Earth System grid. It's the simple is the straight answer. So if you want things from the Palaeoclimate experiment, then you need to go and approach Alan Hayward in Leeds, and he's got a server that's got everything on it. Whilst if you want to get stuff from the deep MIP experiment, which is of the early Eocene, then actually you need to go and contact Paul's colleagues over in Bristol, and probably Dan Lunt to start off with. Is that right, Paul?
Yeah, that's right. So Dan has a copy out, and I think actually that data set is soon going to be actually published online, so you won't even need to actually contact Dan to get access to it.
So yeah, for some of the other experiments that have been run, since there's not a central repository, so I mentioned there's some last deglaciation simulations and some ones of just the Holocene that are running forward, so transient simulations. Those you're going to have to go to the individual researchers to get hold of, because there aren't the single things. And Ellie's replied asking about quaternary interglacials. The last interglacials available, more other ones, you're probably going to need to find individual papers and contact people.
Well, and also go to the PMIP4 website and contact so I'll put that in the yeah, so the PMIP4 website, you can look up who is in charge of the interglacial sub-project, and they would probably be a good person to contact in the first place to find out where the data is.
Yeah, thanks for that. And so give an example between the different models that are part of PMIP4 and those that aren't. The general differences are spatial resolution. And so the models that are part of PMIP4, or really the models that people are building to look at the future, are making use of the greater computing power and zooming in slightly more and having a better spatial resolution. There might be some more complexity in things that are potentially not of any interest in the paleo context, so sort of the atmospheric chemistry associated with various anthropogenic pollutants, for example. There are some interactive carbon cycle models that are not part of they're part of PMIP4 potentially, but they're not going to be run for the future scenarios generally, because those future scenarios have atmospheric concentrations. And so although there are Earth system models with carbon cycles available, they do some slightly different science. And so they're not as readily available through sort of the Earth System Grid Federation style of things.
We've got another question on the LGM about will we get more models?
The answer is yes. I know, so the paper that describes the LGM simulations has been organized by Masa Kageyama, and that has 8 models included in it, of which a couple are 1 or 2 are of a coarser resolution. That means that it wouldn't be fair to try and include their future projections, because they're not new, the future projections, and so they're not included in, so they're just not stored on the Earth System Grid yet, but hopefully will be. And there's at least one Canadian model that has done all the data and it's all sitting there, but sorting out how to get it onto the Earth System Grid Federation is proving a challenge, and so that doesn't exist. And do you know, Paul, about a UK LGM?
I do indeed, because I'm running it, or at least not me, but Kenji Izumi is running a LGM simulation with HadGem 3, and that's still in its early days. It's got to about 100 years now in terms of spinning up the model, and there's still refinements that we need to make. So it takes, running these, particularly these big models that are used in CMIP6, does take some considerable amount of time, even with the biggest computers around. It can take several months to run the simulations, and that's assuming you don't have any problems with changing the boundary conditions, sort of thing. So it's quite a lengthy process. So they will gradually come online. The other thing I'd just comment about is that sort of, particularly related to that sort of resolution issue, it's worth remembering that, you know, when we talk about the lower resolution models, these were models basically used for the previous IPCC assessment. So that, for instance, again, in Massa's paper, we contributed some HADSIM-3 simulations, which are an old model by modern standards. It has to be said, when you compare CMIP5 and CMIP6 and DCMIP3, there's not that much difference between the final conclusions, really. So resolution is important for some aspect, but for mean climate, hasn't changed so much through time. If there's no other questions, then all that is left is to thank you again, Chris, for an excellent talk, giving an idea of what's going on within both PMIP and how to access the data. It encourages me to, I'm a bit of a Luddite, I'm not using Python yet, but I really must get on and use Python. I still write all my code in Fortran. But hopefully many of you will start afresh and will be able to access the data and in particular collaborate with the modelers, because that's really what we're what all modelers enjoy, is the collaboration using the data. So with that, thank you very much, Chris, and thank you, the audience.
Thank you.